Okay, this video is going to go over a couple special electrical circuits. So the first one that we're going to look at is called the DC-DC buck converter, which looks something like the following circuit. So we have a voltage source that's powering this device that is connected to a switch that can switch between two wires, A or B here. On the other side of this switch, we have an inductance that's connected to a capacitor, which is in parallel to our load, our device that's being powered, which is an inductor in this case. So Y is going to be the current of our device. That's what's requiring. So that could be like powering a motor or a fan in this case. And so you can control how fast the switch flips back and forth. And the average of that, that's called the duty cycle D. So if the switch is set at 75% of the time it's at A and 25% of the time it's at B, then our duty cycle D is going to be equal to 0.75. And our duty cycle is something that you control. It is an input in this case. So the simplified way to draw the circuit looks like the following. We just have a box that's labeled DC-DC converter. It has some sort of voltage going in. It has some sort of voltage going out. And it has a current going in and a current going out here. The output of the voltage, our output voltage would be D times V in. It would actually reduce that voltage down. So it'd be if the duty cycle is 75% or 0.75, the output voltage will only be at 0.75 or whatever the input voltage is. And our current in is actually going to be the duty cycle times what's coming out. And that duty cycle is limited between 0 and 1 here. So this is the basic way to represent a DC-DC buck converter. And the name buck comes from it's reducing things down. A boost converter would actually increase your voltage output, but a buck converter decreases it. So the other element that we have, or that we're going to focus on, are operational amplifiers, or op-amps for short. So an op-amp is a special circuit that's used for measurement and control systems. And these can be used to increase observable voltages by some sort of gain here. So if we have a circuit that looks like this is what our op-amp is. It's a little bit of a mess, but I'm going to show a simpler way to draw this out. But we have some sort of source input voltage coming in. We have a voltage coming out here. We have two resistances here, our input and our F, or output resistances, I'm going to call them. And then our op-amp here, which has some sort of gain, and that's going to adjust essentially this voltage, or not this voltage here. It's going to adjust what this output has here. And this V1 here, this is our voltage at this point with respect to our ground. So that's V1 is what I'm going to call that. So for this op-amp, a simpler way to draw this out would be to replace that big ugly triangle with just an external node right here for I3. Our voltage is still V1 is across this. And then this op-amp here, that is essentially like acting like a voltage source where we have negative G times that V1 coming across right here to produce this output voltage. And so there are a couple big assumptions with op-amps. The first one being that an op-amp can draw very little current to run. So let's say that I3 is approximately equal to 0, which kind of makes sense. This is kind of going nowhere at this point. And then our op-amps also have high gain. So that gain can approach infinity, essentially. So if we draw the circuit out one more time in an even more simplistic version, we're going to have, and this is just found by shifting all of our elements around, our input voltage here is connected in series to our input resistance, just like our output voltage is connected to our RF, or output resistance here. And then we have this V1 here, which is directly related to VO by that gain coming across this point right here. And using the assumptions that we have, I'm not going to go through all the math here, but maybe we'll do it in class if anyone requests it. That output voltage is going to end up just being a straight up ratio between RF and RI here. And you can kind of see, just looking at the symmetry here, that how that kind of almost makes sense to figure out what that output voltage is here. The only difference is that it actually inverts, doesn't invert the voltage, it makes it negative. So our output voltage is equal to our input voltage times RF over RI, but the negative of that. And that is it for our special electrical circuits.